I'm here. I made it. Uh, don't know how long we're gonna be able to go tonight. Not feeling the best. But I think okay. So I look back at the last lesson we did, and we didn't do the quiz time. Skipped it, and then I was like, "Oh, it'll be a good refresher," and then I didn't come back for a year. So be a little difficult to just do the quiz right now. I'm like, I don't really know. So I think what would be best, because the way the lessons are laid out, is we just continue reading, and then when we get confused, they have good enough links to go back, and we'll refresh ourselves as we go. I know, I'm like, I don't know the controls. What was I doing last? Yeah. So I was like, I was trying to. The big part of doing this is that I have a log of all the lessons, so I need to like sit down and rewatch all of it, listen through it. But we're gonna start with a typing test. We're gonna do it, and it's been a while. All right, how y'all doing? Does that look okay? I mean, yeah, I think that shows everything. All right. It's gonna be. Oh wait. We want the mic to cover it so I don't look. All right. Oh crap! I'm like, where the hell is V? You gotta start with V. All right. Okay. No! Already out the gate. Trying to like keep my fingers like on the home row keys, like that kind of typing. Oh god. Ah. Fuck. Hey. Okay, hey. What's happening? Oh, okay. That's oh shit. Okay. Whoa. Okay. Shit. Damn it. Son of a bitch. What? Okay. Nope. Oh, fuck it. It's not shift. That's what. Okay. Do one at the beginning and then one at the end. Oh my god. Ah. Okay.
Where the rats?
Fuck. The underscore is really getting me. Fuck. What the fuck? where it's getting all funny with me. Ah. Q? Wait, what the fuck? Q. Ah. Oh my god. Honestly, I'm doing a lot better than I was expecting. Not like I've been typing with the home row keys in my off time. Hello? What is happening? Why is it type like what is it doing? Doing like a drop down over here. Type. Do. Fuck, I look. Oh my god. That's terrible. Yeah. Jesus. Okay. Screw that. 4.1. I'm trying to stop. Jesus Christ. Okay. 4.1. Introduction to fundamental data types. Bits, bytes, and memory addressing. In Lesson 1.3, Introduction to Objects and Variables, we talked about the fact that variables are names for a piece of memory that can be used to store information. To recap briefly, computers have random access memory that is available for programs to use. When a variable is defined, a piece of that memory is set aside for that variable. The smallest unit of memory is a binary digit, also called a bit, which can hold a value of 0 or 1. You can think of a bit as being like a traditional light switch. Either light is off or it's on. There is no in between. If you were to look at a random segment of memory, all you would see is zeros and ones, or some combination thereof. Memory is organized into sequential units called memory addresses, or addresses for short. I need to zoom in. There we go. Enhance. Just make sure. Okay, this looks. Okay, everything I see is what you can see. Okay. Memory is organized into sequential units called memory addresses, or addresses for short. Similar to how a street address can be used to find a given house on a street, the memory address allows us to find and access the contents of a memory at a particular location. Perhaps surprisingly, in modern computer architectures, each bit does not get its own unique memory address. This is because the number of memory addresses is limited, and the need to access data bit by bit is rare. Instead, each memory address holds 1 byte of data. A byte is a group of bits that are operated on as a unit. The modern standard is that a byte is comprised of 8 sequential bits. Key insight. In C++, we typically don't work with byte-sized chunks of data. Okay, what do you work with? The following picture shows some sequential memory addresses, along with the corresponding byte of data. See, now this is like stuff I watch a lot of videos on like like altering like the memory addresses for like speed runs so that you can like skip a level or whatever. And I look at this shit and I'm just like, how are people looking at just like a bunch of like zeros and like numbers, like hex codes and stuff, and it's like, oh yeah, we need to change this, and like change it to what? Like, what? How are you doing that? I feel like this is part of that. As an aside, some older or non-standard machines may have bytes of a different size, from 1 to 48 bits. However, we generally do not worry about these, as the modern de facto standard is that a byte is 8 bits. For these tutorials, we'll assume a byte is 8 bits. It's like, this is like the fact that it gets as small as like it's ones and zeros. It's going that fast. I can do all of this just on ones and zeros. I'm like, what? All right, data types. Because all data on a computer is just a sequence of bits, we use a data type, often called a type for short, to tell the compiler how to interpret the contents of memory in some meaningful way. If you've already seen one example of a data type, the integer, when we declare, sorry, I read that weird. You've already seen one example of a data type, the integer. An abacus. When we declare a variable as an integer, we are telling the compiler the piece of memory that this variable uses is going to be interpreted as an integer value. When you give an object a value, the compiler and CPU take care of the encoding your value into the appropriate sequence of bits for that data type, which are then stored in memory. Remember, memory can only store bits. For example, if you assign an integer object the value 65, that value is converted to the sequence of bits 0, 1, 0, 0, 0, 0, 0, 1, and stored in the memory assigned to the object. Conversely, when the object is evaluated to produce a value, that sequence of bits is reconstituted back into the original value, meaning that 0, 1, 0, 0, 0, 0, 0, 1 is converted back into the value 65. Fortunately, the compiler and CPU do all the hard work here, so you generally don't need to worry about how values get converted into bit sequences and back. All you need to do is pick a data type for your object that best matches your desired use. Okay. Right. So all that's happening on the CPU. We don't need to worry about it. But that's what the program is running when I'm telling it to do stuff. Part of what it's running is changing it to binary and then back again. Okay. Fundamental data types. C++ language comes with many predefined data types available for your use. Most basic of these types are called the fundamental data types, informally sometimes called basic types or primitive types. Here is a list of the fundamental data types, some of which you have already seen. Okay, we got floats, doubles, long double, bool, character, short integer, integer, long integer, void. I don't know what these are. This chapter is dedicated to exploring these fundamental data types in detail, except nullity, which we'll discuss when we talk about pointers. Okay, a null pointer. Okay. Integer versus integral types. In mathematics, an integer is a number with no decimal or fractional part, including negative and positive numbers and zero. The term integral has several different meanings, but the context of C++ is used to mean like an integer. C++ standard defines the following terms. Standard integer types are short, int, long, including their signed and unsigned variants. The integral types are bool, the various character types, and the standard integer types. All integer types are stored in memory as integer values, but only the standard integer types will display as an integer value when output. We'll discuss what bool and the character types do when output in their respective lessons. What the fuck? We'll discuss what bool and the character types do when output in their respective lessons. Why does that sound weird at first? Okay. C++ standard also explicitly notes that integer types is a synonym for integral types. However, conventionally, Jesus Christ, integer types is more often used as a shorthand for these standard integer types instead. Also note that the term integral types only includes fundamental types. This means non-fundamental types such as enum and enum class are not integral types, even when they are stored as an integer. Case of enum displayed as 1, 2. What? I don't know what enum is. Give me a second. I think they're just saying that integers are stored as integers. Is that too simple? I feel like I didn't get that. There's standard integer types. And then there's an integral type. What? So standard integer types are also integral types. Like these are under the umbrella of this, right? Don't take a year between the lessons. I'm like, what are we talking about here? All right, we'll move on. Other sets of types. C++ contains 3 sets of types. The first 2 are built into the language itself and do not require the inclusion of a header to use. The fundamental data types provide the basic and essential data types. That's weird. Provide the basic? The compound data types provide more complex data types and allow for the creation of custom user-defined types. Cover these in lesson 12.1, Introduction to Compound Data Types. The distinction between the fundamental and compound types isn't all that interesting or relevant, so it's generally fine to consider them as a single set of types. The third and largest set of types is provided by the C++ standard library. Because the standard library is included in all C++ distributions, these types are broadly available and have been standardized for compatibility. Use of the types in the standard library require the inclusion of the appropriate header and linking in the standard library. Okay, I know what they're saying here. They're saying that integer and stuff like that are included in the standard library. Because they provide the most basic, the most essential. The basic. Okay. Nomenclature. The term built-in type is most often used as a synonym for the fundamental data types. However, Strausstrup, I forgot about Strausstrup. However, Strausstrup and others use the term to mean both the fundamental and compound data types, both of which are built into the core language. Since this term isn't well defined, we recommend avoiding it accordingly. Okay. A notable omission from the table of fundamental types above is a data type to handle strings, a sequence of characters that's typically used to represent text. This is because in modern C++, strings are part of the standard library, although we'll be focused on fundamental types in this chapter. Because basic string usage is straightforward and useful, we'll introduce strings in the next chapter. In lesson 5.7, Introduction to Standard String. The T suffix, I was wondering that, the pointer T, means type. Okay. Many of the types defined in the newer version of C++ use a _T suffix. This suffix means type and it's a common nomenclature applied to modern types. If you see something with a _T suffix, it's probably a type, but many types don't have an _T suffix, so this isn't consistently applied. Let's go into the void. Void is the easiest of the data types to explain. Basically, void means no type. Void is our first example of an incomplete type. An incomplete type is a type that has been declared but not yet defined. The compiler knows about the existence of such types, but does not have enough information to determine how much memory to allocate for objects of that type. Void is intentionally incomplete since it represents the lack of a type and thus cannot be defined. Incomplete types cannot be instantiated. You cannot divide by 0. Void value won't work. Variables can't be defined with incomplete type void. Void is typically used in several different contexts. Functions that do not return a value. Most commonly, void is used to indicate that a function does not have a return value. We got write value. Void here means don't return a value. Value of x is x. No return statement because this function doesn't need a return value. Just need to output it. So it doesn't need, okay. It's void because this is outputting a variable in the function. So it's already done with the variable. It doesn't need to send it anywhere. Right? Am I getting that right? If you use a return statement to try and return a value in such a function, a compile error will result. Trying to return something in a void, it's like, girl, can't do that. Visual Studio 2017, this produced the error. Okay. deprecated. I'm like, is that the word? Deprecated. I wanted to say depreciated. I was like, that is not it. Deprecated. Functions that do not take parameters. Oh. And C, void is used as a way to indicate that a function does not take any parameters. Although this will compile in C++, for backwards compatibility reasons, this use of keyword void is considered deprecated in C++. Following code is equivalent and preferred in C++. Oh, because I did an int and then it's like just voided over here, the value. Weird. Empty function parameters is an implicit void. Okay. Interesting. I think that's why it was like confusing me. Like it, I was like, it should. What are you doing? Okay. Best practice: use an empty parameter instead of void to indicate that a function has no parameters. Okay. Other uses of void. The void keyword has a third, more advanced use in C++ that we cover in section 19.5, void pointers. Since we haven't covered what a pointer is yet, you don't need to worry about this case for now. Let's move on. Okay. Four 4.3 Object sizes and the size of operator. Object sizes. As you learned in lesson 4.1, Introduction to Fundamental Data Types, memory on modern machines is typically organized into byte-sized units, with each byte of memory having a unique address. Up to this point, it has been useful to think of memory as a bunch of cubbyholes or mailboxes where we can put and retrieve information, and variables as names for accessing those cubbyholes or mailboxes. However, this analogy is not quite correct in one regard. Most objects actually take up more than one byte of memory. A single object may use 1, 2, 4, 8, or even more consecutive memory addresses. The amount of memory that our object uses is based on its data type. Because we typically access memory through variable names and not directly via memory addresses, the compiler is able to hide the details of how many bytes a given object uses from us. When we access some variable x in our source code, the compiler knows how many bytes of data needs to be retrieved based on the type of variable x, and will output the appropriate machine language code to handle that detail for us. Even so, there are several reasons it is useful to know how much memory an object uses. First, the more memory an object uses, the more information it can hold. A single bit can hold two possible values, a 0 or a 1. 2 bits can hold 4 possible values. Ooh. Okay, I kind of do feel like this helps me a little bit. Okay. 3 bits can hold 8 possible values. Interesting. To generalize, an object with n bits, where n is an integer, can hold 2 to the power of n. 2 to the power of n, also commonly written, okay. Can hold 2 to the power of n unique values. Therefore, with an 8-bit byte, a byte-sized object can hold 2 to the power of 8, 256, dude, like colors. 256 different values. An object that uses 2 bytes can hold 2 to the power of 16. Jesus, different values. Okay. Thus, the size of the object puts a limit on the amount of unique values it can store. Objects that utilize more bytes can store a larger number of unique values. We'll explore this further when we talk more about integers. Second, computers have a finite amount of free memory. Every time we define an object, a small portion of that free memory is used for as long as the object is in existence. Because modern computers have a lot of memory, this impact is usually negligible. However, for programs that need a large amount of objects or data, a game that is rendering millions of polygons, the difference between 1 byte and 8 byte objects can be significant. You gotta bake your lighting. Key insight: new programmers often focus too much on optimizing their code to use as little memory as possible. In most cases, this makes a negligible difference. Focus on writing maintainable code and optimize only when and where the benefit will be substantive. I hate it so much. It's so bad. Fundamental data type sizes. The obvious next question is, how much memory do objects of a given data type use? Perhaps surprisingly, the C++ standard does not define the exact size in bits of any of the fundamental types. Instead, the standard says the following. An object must occupy at least 1 byte so that each object has a distinct memory address. A byte must be at least 8 bits. The integral types, character, short, int, long, and long. I really want to know what long is. Have a minimum size of 8, 16, 16, 32, and 64 bits respectively. Character and character 8 underscore type are exactly 1 byte and at least 8 bits. It's long. I'm like, I don't think I've gone over that yet. If we have, I'm like, well, we're going over the types. I'm sure we're talking about integers right now, so we'll figure it out. long. Nomenclature. When we talk about the size of a type, we really mean the size of an instantiated object of that type. That's what she said. In this tutorial series, we will present a simplified view by making some reasonable assumptions that are generally true for modern architectures. A byte is 8 bits. Memory is byte addressable. We can access every byte of memory independently. Floating point support is IEEE 754 compliant. I don't what does that mean? We are on a 32-bit or 64-bit architecture. Okay, I do get that. Given the above assumptions, we can reasonably state the following. Okay. I guess it's like we know how many bytes. Oh, minimum size and typical size. That's so strange. It's like average. Okay. Tip. For maximum portability, you shouldn't assume that objects are larger than the specified minimum size. Alternatively, if you want to assume that a type has some non-minimum size, that an integer is at least 4 bytes, you can use static assert. I don't know what that sounds like a Pokemon move. I'm just like, static assert. Have the compiler fail a build if it's compiled on an architecture where this assumption is not true. We will cover how to do this in lesson 9.6, assert and static assert. Related content. You can find more information about what the C++ standard says about the minimum size of various types here. The size of operator. In order to determine the size of data types on a particular machine, C++ provides an operator named sizeOf. SizeOf operator is a unary operator that takes either a type or a variable and returns the size of an object of that type in bytes. You can compile and run the following program to find out how large some of your data types are. Let's do it. And go. There, I was like, what's going on? Okay. A byte is 8 bits. Oh wait, we can go look at the typical. Kind of covering a little bit, but okay. Cool. 1 byte. Character, 1 byte. And then short, 2 bytes. Int. 4, so we're at what's typical. Our long is 4. So 4 or 8, and then long's 8, but it's always 8. Minimum will be 8. Okay. Float 4. 8, 8. Long double. 8, 12, or 16, and minus 8. Is that good? Okay. Output of the author's machine. I think that was the same. Pretty sure. Your result may vary based on compiler, computer architecture, OS, compilation settings, 32-bit versus 64-bit, etc. Trying to use sizeOf on an incomplete type, such as void, will result in a compilation error. We don't need to read that. GCC. You can also use the sizeOf operator on a variable name. X is size of X bytes. Okay. X is 4 bytes. I see. So the sizeOf operator is asking the machine how much memory are you using? How many bytes is this? How many bytes are we using up here? Right? Trying to use sizeOf. Did I read that? Yeah, I did. Okay. For advanced readers, sizeOf does not include dynamically allocated memory used by an object. We discuss dynamic memory allocation in a future lesson. Fundamental data type performance. On modern machines, objects of the fundamental data types are fast, so performance while using or copying these types should generally not be a concern. As an aside, you might assume that types that use less memory would be faster than types that use more memory. This is not always true. CPUs are often optimized to process data of a certain size, like 32 bits, and types that match that size may be processed quicker. On such a machine, a 32-bit int could be faster than a 16-bit short or an 8-bit character. See. All right. 4.4. Signed integers. An integer is an integral type that can represent positive and negative whole numbers, including 0. Ooh. Signed integers. Okay. Positive and negative whole numbers, including 0. C++ has 4 primary fundamental integer types available for use. Key difference between the various integer types is that they have varying sizes. The larger integers can hold bigger numbers. A reminder, only C++ only guarantees that integers will have a certain minimum size, not that they will have a specific size. See lesson 4.3, object sizes, and the size of operator. What are we on? For information on how to determine how large each type is on your machine. Got him. Get out of here. It's been a lot of just best views. Like, I feel like I was streaming a few years ago. It just used to be a little bit more variety going on with the spam. As an aside, technically the bool and character types are considered to be integral types because these types store their values as integer values. For the purpose of the next few lessons, we'll exclude these types from our discussion. Oh gosh. Honestly, that would be crazy if I could like figure out their IP and then like do like a DDoS. And to have that be automated, that would be really like dangerous. Signed integers. When writing negative numbers in everyday life, we use a negative sign. For example, -3 means -3. We'd also typically recognize +3 as +3, though common convention dictates that we typically omit plus prefixes. This attribute of being positive, negative, or 0 is called the number sign. By default, integers in C++ are signed, which means the number's sign is stored as a part of the value. Therefore, a signed integer can hold both positive and negative numbers, and 0. In this lesson, we'll focus on signed integers. We'll discuss unsigned integers, which can only hold non-negative numbers in the next lesson. Defining signed integers. Here's a preferred way to define the 4 types of signed integers. Oh, short as? Wait. LL. Interesting. Although short int, long int, and long int will work, we prefer the short names for these types that do not use the int suffix. Okay. In addition to being more typing, adding the int suffix makes the type harder to distinguish from variables of type int. That's like just int, yeah. This can lead to mistakes if the short or long modifier is inadvertently missed. The integer types can also make optional sign keyword, which by convention is typically placed before the type name. Okay. Like, okay, wait. Did I miss, like, what does signing even mean? Sign, which means the number sign. Number sign is stored as a part of the value. Okay. However, this keyword should not be used as it is redundant since integers are signed by default. Best practice. Prefer the shorthand types that do not use the int suffix or sign prefix. Okay. Signed integer ranges. As you learned in the last section, a variable with n bits can hold 2 to the power of n possible values. But which specific values? We call the set of specific values that a data type can hold its range. The range of an integer variable is determined by 2 factors: its size in bits and whether it's signed or not. For example, an 8-bit signed integer has a range of -128 to 127. That means an 8-bit signed integer can store any integer value between -128 and 127, inclusive, safely. Okay. Here's a table containing the range of signed integers of different sizes. Okay. I do know that, like, that's why, like, okay, 32-bit, like, with Windows 7, Windows XP or whatever, there's like 32-bit, 64-bit. I don't know really anyone with 32-bit anymore, but the big thing with 64-bit is that, like, the CPU can move more data at a time. Like, it's twice as fast, I'm assuming. For the math inclined, an n-bit signed variable has a range of -2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. Thank you. For the math non-math inclined, use the table. Okay. What are you doing? We're reading through, I guess I should say, yeah. This is learncpp.com. It is a free website. There are ads on the website. I have it ad blocked for the stream, but they emphasize a lot, don't use ad blocker. And so I'm going to stress to you, don't use ad blocker. I'm just afraid. I don't want to be just showing ads on stream all day long, you know? 2 to the 1 to the 2 to the 3. Yeah, it's like, it says use the table, and I'm like, okay. I'm like, I still don't know what we're doing, but okay. Yeah, and honestly, I would be honest, because it's been a year since we did the last lesson, some of this stuff is like, it's not really retaining, but definitely I feel like the rust coming off, you know? I am trying to develop video games, and you really can't do that without learning how to code. So yeah, I'm like, it's like, you gotta do it, you know? But honestly, it's people were saying, I mean, I guess I haven't gotten super into it yet, but C++ doesn't seem all that crazy. Maybe we're starting to get into like because it's like memory, yeah, like how it like messes with the memory or something gets a little weird. But from what I know of programming, this has all been basically just teaching me programming again, except that's the thing I really like about this website. It is very thorough, that I feel like I'm going over things I learned in college, and it's like I'm actually like sitting and retaining it and learning it. It's like it's being said in a mostly like easy language that like I can get. It's a little bit less textbook. I don't know. For advanced readers, the above ranges assume two's complement binary representation. This representation is the de facto standard for modern architectures, as it is easier to implement in hardware and is now required by the C++20 standard. We discussed two's complement in lesson 0.4? Doesn't that look like a 0? Oh, because there's like, it's like extra lessons later, I think. Converting integers between binary and decimal representation. In prior standards, sign magnitude and one's complement representations were permitted for historical reasons. Ooh. Such representations produce values in the range -2 to the power of n minus 1 minus 1, 2 plus 2 to the power of n minus 1 minus 1. Okay. Overflow. What happens if you try to assign the value 140 to an 8-bit signed integer? This number is outside the range of that 8-bit signed integer can hold. The number 140 requires 9 bits to represent. 8 magnitude bits and 1 sign bit, but we only have 8 bits. 7 magnitude bits and 1 sign bit available is an 8-bit. What am I reading? Overflow. Okay. The C++20 standard makes this blanket statement. If during the evaluation of an expression, the result is not mathematically defined or not in the range of representable values for its type, behavior is undefined. Colloquially, this is called overflow. During the evaluation of an expression, if while they're evaluating the expression, the result's not mathematically defined or not in the range of representable values for its type, the behavior is undefined, which means you're getting an error. Okay. Therefore, assigning value 140 to an 8-bit signed integer will result in undefined behavior. If an arithmetic operation, error is not undefined behavior. Undefined behavior means every time you run it, it's going to be something. Like you can't depend on the code, right? But it doesn't throw an error. I don't know. If an arithmetic operation, such as addition or multiplication, attempts to create a value outside the range that can be represented, this is called integer overflow or arithmetic overflow. For signed integers, integer overflow will result in undefined behavior. The maximum, assume 4 bytes integers. Maximum value of a 4-byte signed integer. Integer overflow, undefined behavior. Yeah, let's run it. What we got? That's what it said it would do, right? On the author's machine, the above printed. However, because the second output is the result of undefined behavior, the value output may vary on your machine. It's kind of like, do I do... Oh, wait. No, yeah, that's what I got. Wait, whoa, what? I was like, what? Whoa. That actually, like, that's terrible. That was some undefined behavior. Oh no. You know, okay. I was watching, gosh, I don't remember. Oh no, I haven't retained enough to talk about it, but someone who worked for Oracle, he was, okay. He like volunteered or something. Like he worked for Oracle. He wrote, oh, okay, that's what it was. Minecraft. What Java uses for logs. Okay, it's coming back to me now. What Java uses for logs, which Minecraft uses for like their server log, there was a vulnerability in it where the log could be used to like, I think like inject code. I don't really know. There was a vulnerability and it was like huge and terrible and horrible. Like it was like a widespread issue. And the guy who wrote the code, it was like, because it was open source software. That's what the whole like conversation was about, was on like open source software. And you know, he felt that like at the time it's like, oh, like this is, you know, I'm doing this work and people can use it for free, like this is nice. But then it's like now there's vulnerabilities and people need help, and it's like you have to like figure it out. And I don't know, it was just the idea of like you're trying to do something good and nice and you did something for free and it's like fucked with shit, and it's like, whoops. I'm sorry. I thought I wrote that good. It was, I guess, like talking about like the dangers of like open source software. It was an interesting idea. So I had always thought of it as like, I don't know, like not a lot of downsides, but I don't know. For advanced readers, we cover what happens when unsigned integers overflow in less than 4.5 unsigned integers and why to avoid them. In general, overflow results in information being lost, which is almost never desirable. If there is any suspicion that an object might need to store a value that falls outside its range, use a type with a bigger range. Okay. Integer division. When dividing two integers, C++ works like you'd expect when the quotient is a whole number. This produces the expected result. We're dividing 20 by 4, and we need 5. Okay. Let's look at what happens when an integer division causes a fractional result. Oh my gosh. Because it's an int, you can't get a fraction. It's got to round up. When doing division with two integers, called integer division, C++ always produces an integer result. Since integers can't hold fractional values, any fractional portion is simply dropped. Not rounded. It's dropped. Concatenated. I don't know. I don't know if that's the word. Taking a closer look at the above example, 8 divided by 5, I'm like 8 out of 5. 8 divided by 5 produces the value 1.6. The fractional part, 0.6, is dropped, and the result of 1 remains. Alternatively, we can say 8 divided by 5 equals 1 remainder 3. The remainder is dropped, leaving 1. Similarly, negative 8 divided by 5 results in the value negative 1. Warning! Be careful when using integer division, as you will lose any fractional parts of the quotient. However, if that's what you want, integer division is safe to use, as the results are predictable. If fractional results are desired, we show a method to do this in lesson 6.2, arithmetic operators. Quiz time! Oh God, I wasn't ready. What would the range of a 5-bit signed integer be? Damn it. Six, right? Like, it'd be 6 bits. Was that the question? What, that's what I don't know. What would the range? What did we just say? What were we just talking about? The range. What would the range be? Maybe that? Or do I need to do this? N is 5. I don't wanna. 6. Okay, give me the answer. A 5-bit number can support 2 to the power 5 equals 32 unique values. Yeah, we had to put it in the formula. I wasn't going to do that. For a signed integer, these are split almost evenly amongst positive and negative numbers, with negative receiving an extra value. So the range would be negative 16 to 15. Another way to think of this, one of the 5 bits is required to hold the sign. That leaves 4 bits for the magnitude. With 4 bits, we have 16 unique values available. On the negative side, these magnitude bits represent values negative 1 to negative 16. I am not retaining any of this. On the negative side, non-negative side, these magnitude bits represent values 0 to 15. The non-negative side has 1 less value of range because it includes 0. You can't delete your own message. I mean, you can. Just erase all your typos. Okay. So the range would be negative 16 to 15. That's the range. That's the range in, like, memory. Like, that's how much space it would need to put the value of not negative 5, sorry, just 5, positive 5. I feel like I'm just like not getting this. What is the result of 13 divided by 5? I don't feel good. 2, remainder 3. The remainder is dropped, leaving 2. It's going to be negative 2. Got 1. Okay. I really feel like I'm not getting what the range is, and so I feel bad moving on. Again, like the main thing, I try to read through it so that I can then later listen to it and study it later. Integers? It's 32 integers? I thought 32 bits. I feel like it's bits. Excuse me. The range of bits that can be used for positive 5. Right? I feel like I got it thinking it like that. Okay. 4.5, unsigned integers, and why to avoid them. They told us about this lesson. Unsigned integers. In the previous lesson, signed integers, we covered signed integers, which are a set of types that can hold positive and negative whole numbers, including 0. C++ also supports unsigned integers. Unsigned integers are integers that can only hold non-negative whole numbers. Right. So only positive numbers because it can't hold the positive or negative sign. So it's an unsigned integer. I think we already got this lesson down. We got it. Defining unsigned integers. To define an unsigned integer, we use the unsigned keyword. By convention, this is placed before the type. Okay. Unsigned integer range. A 1-byte unsigned integer has a range of 0 to 255. Compare this to the 1-byte signed integer range of negative 128 to 127. Both can store 256 different values, but signed integers use half their range for negative numbers, whereas unsigned integers can store positive numbers that are twice as large. Here's a table showing the range for unsigned integers. Starting at 0. Because we can't go into the negative. Okay. An n-bit unsigned variable has a range of 0 to 2 to the power of n minus 1. When no negative numbers are required, unsigned integers are well suited for networking and systems with little memory. because unsigned integers can store more positive numbers without taking up extra memory. Remembering the terms signed and unsigned. New programmers sometimes get signed and unsigned mixed up. The following is a simple way to remember the difference. In order to differentiate negative numbers from positive ones, we use a negative sign. Come on. If a sign is not provided, we will assume a number is positive. Consequently, an integer with a signed integer, can tell the difference between positive and negative. An integer without a sign, an unsigned integer, assumes all values are positive. Okay. Unsigned integer overflow. What happens if we try to store the number 280, which requires 9 bits to represent, in a 1 by 8-bit unsigned integer? The answer is overflow. Author's note. Oddly, the C++ standard explicitly says a computation involving unsigned operands can never overflow. What? This is contrary to general programming consensus that integer overflow encompasses both signed and unsigned use cases. Given that most programmers would consider this overflow, we'll call this overflow despite the C++ standard statements to the contrary. Okay. I'm really not understanding that. It's like they're saying that C++, like the rules of C++ say that like an unsigned fucking operation can never overflow. But then he's saying, well, yeah, they can. So we're just gonna ignore them. I was like, what? Why does it say that though? Okay. If an unsigned value is out of range, it is divided by 1 greater than the largest number of the type, and only the remainder kept. The number 280 is too big to fit in our 1 byte range of 0 to 255. 1 greater than the largest number of the type is 256. Therefore, we divide 280 by 256, getting 1 remainder, 24. The remainder 24 is what's stored. Okay. Here's another way to think about the same thing. Any number bigger than the largest number representable by the type simply wraps around. Something called, I guess that's why they would say it wouldn't overflow, because it would do the wraparound. It would do a wraparound. Sometimes called modulo wrapping. 255 is in range of a 1 byte integer, so 255 is fine. 256, however, is outside the range, so it wraps around to the value 0. 257 wraps around to the value 1. 280 wraps around to the value 24. Oh, okay. Let's take a look at this using 2 byte shorts. Largest 16-bit unsigned value possible. Hang on, I'm gonna sneeze. Yeah. Thank you. Donkey. What do you think the result of this program will be? Okay. Man, I don't know. X is now a wraparound. They're gonna wrap around a lot. I don't know. Let's go ahead and plug it in. Oh. ¿Por qué? No. Overflow or truncation. You'll need to disable treat warnings as error to run the program. Oh no, I don't want to do that again. Okay, whatever. We're not doing that. It's like so in the settings to turn that off, I think. It's possible to wrap around the other direction as well. 0 is representable in a 2-byte unsigned integer, so that's fine. -1 is not representable, so it wraps around to the top of the range, producing the value 65535. -2 wraps around to 65534, and so forth. X was 0. Okay. The above code triggers a warning in some compilers because the compiler detects that the integer literal is out of range for the given type. If you want to compile the code anyway, temporarily disable treat warnings as errors. As an aside, most notable bugs in video game history happen due to wraparound behavior with unsigned integers. In an arcade game, Donkey Kong, it is not possible to go past level. Yes, okay. Before I read it, the level goes too fast that you can't. It's impossible to get to the top, right? It's not possible to go past level 22 due to an overflow bug that leaves the user with not enough bonus time to complete the level. In the PC game Civilization, Gandhi was known for often being the first one to use nuclear weapons, which seems contrary to his expected passive nature. Players had a theory that Gandhi's aggression setting was initially set at 1, but if he chose a democratic government, he'd get a -2 aggression modifier, lowering his current aggression value by 2. This would cause aggression to overflow to 255, making him maximally aggressive. However, more recently, Sid Meier clarified that this wasn't actually the case. Okay. Yeah, I had watched a video about like soft locks in games, and that was one of them. Was Donkey Kong? It's like can't get past it. The controversy over unsigned numbers. Many developers and some large development houses, such as Google, believe that developers should generally avoid unsigned integers. Oh. This is largely because of two behaviors that can cause problems. First, with signed values, it takes a little more work to accidentally overflow the top or bottom of the range because those values are far from 0. With unsigned numbers, it is much easier to overflow the bottom of the range because the bottom of the range is 0, which is close to where the majority of our values are. Consider the subtraction of two unsigned numbers, such as 2 and 3. Yeah, honestly, like that's like the thing with this, like reading through this is like, oh, like that's how that game broke. I love that. Two minus 3. Incorrect. You and I know that 2 minus 3 is -1, but -1 can't be represented as an unsigned integer, so we get overflow and the following result. Another common unwanted wraparound happens when an unsigned integer is repeatedly decremented by 1 until it tries to decrement to a negative number. You'll see an example of this when loops are introduced. Oh, God. Second, and more insidiously, the unexpected behavior can result when you mix signed and unsigned integers. In C++, if a mathematical operation, arithmetic, or comparison has one signed integer and one unsigned integer, the signed integer will usually be converted to an unsigned integer, and the result will thus be unsigned. For example, assume int is 4 bytes. 2 minus 3. Yeah, I'm like, didn't we just do this exact same thing? In this case, if U is signed, the correct result would be produced. But because U is unsigned, which is easy to miss, S gets converted to unsigned, and the result, -1, is treated as an unsigned value. Since -1 can't be stored in an unsigned value, we get overflow and an unexpected answer. Here's another example of where things go wrong. Okay. -1 is implicitly converted. Jeez. And this is less than 1 is false. -1 is less than 1. This statement executes. This prints 1 is less than -1 because it thinks it's really this, right? This program is well formed, compiles, and is logically consistent to the eye, but it prints the wrong answer. And while your compiler should warn you about signed-unsigned mismatch in this case, the compiler will also generate identical warnings for other cases that do not suffer from this problem. When both numbers are positive, making it hard to detect when there is an actual problem. Like when both numbers are positive, making it hard to detect when there's an actual problem. Related content. We cover the conversion rules that require both operands and certain binary operations to be the same type in lesson 10.5, arithmetic conversions. We cover if statements in upcoming lesson 4.10, introduction to if statements. Additionally, there are other problematic cases that are challenging to detect. Consider the following. Can you consider the following, please? Run some code X times. Assume int. Okay. The author of Do Something was expecting someone to call this function with only positive numbers. But the caller is passing in -1, clearly a mistake, but 1 made regardless. What happens in this case? Signed argument of -1 gets implicitly converted to an unsigned parameter. -1 isn't in range of an unsigned number, so it wraps around to big number. Then your program goes ballistic. Even more problematically, it'd be hard to prevent this from happening, unless you've configured your compiler to be aggressive about producing signed, unsigned conversion warnings. And you should. Your compiler probably won't even complain about this. All these problems are commonly encountered, produce unexpected behavior, and are hard to find, even using automated tools designed to detect problem cases. Given the above, the somewhat controversial best practice that we'll advocate for is to avoid unsigned types, except in specific circumstances. Best practice. For signed numbers over unsigned numbers for holding... Favor signed numbers over unsigned numbers for holding quantities, even quantities that should be non-negative, and mathematical operations. Avoid mixing signed and unsigned numbers. Okay. Related content, additional material in support of the above recommendations. Excuse me. So when should you use unsigned numbers? There are still a few cases in C++ where it's necessary to use unsigned numbers. First, unsigned numbers are preferred when dealing with bit manipulation, covered in Chapter O. It's capital O, not 0. They are also useful when well-defined wraparound behavior is required, useful in some algorithms like encryption and random number generation. Second, use of unsigned numbers is still unavoidable in some cases, mainly those having to do with array indexing. We'll talk more about this in lessons on arrays and array indexing. I think it's because the array index is limited to that 256 number or whatever. So you have to overflow it or whatever if you need to do an array, right? Also note that if you're developing for an embedded system like an Arduino or some other processor memory limited contexts, use of unsigned numbers is more common and accepted, in some cases unavoidable for performance reasons. Interesting. Uh, 4.6, what's... Jesus. 11, I feel like... Oh gosh, introduction to if statements. I feel like we should not do that one yet, right? That'll be for next time. Let me know. We'll just keep going and see, because I feel okay right now. 4.6. Fixed width integers and size _t type. In the previous lessons on integers, we covered that C++ only guarantees that integer variables will have a minimum size, but they could be larger, depending on the target system. For example, an int has a minimum size of 16 bits, but it's typically 32 bits on modern architectures. If you assume an int is 32 bits because that's most likely, then your program will probably misbehave on architectures where int is actually 16 bits. Since you will probably be storing values that require 32 bits of storage in a variable with only 16 bits of storage, which will cause overflow or undefined behavior. For example, this overflows if int is 16 bits. Okay, if int is 32 bits, what will this print? On a machine where int is 32 bits, the value 32768 fits within the range of an int, and therefore it can be stored in X without issue. On such a machine, this program will print 32768. However, on a machine where int is 16 bits, the value 32768 does not fit within the range of a 16-bit integer, which has a range. Okay, I'm not reading all these numbers. On such a machine, x equals x plus 1, which will cause overflow, and the value negative 32768 will be stored in x and then printed. Instead, if you assume an int is only 16 bits to ensure your program will behave on all architectures, then the range of values you can safely store in an int is significantly limited. And on systems where int is actually 32 bits, you're not making use of half of the memory allocated per int. Key insight. In most cases, we only instantiate a small number of int variables at a time, and these are typically destroyed at the end of the function in which they are created. In such cases, wasting 2 bytes of memory per variable isn't a concern. The limited range is a bigger issue. However, in cases where a program allocates millions of int variables, wasting 2 bytes of memory per variable can have a significant impact on the program's overall memory usage. Why isn't the size of the integer types fixed? The short answer is that this goes back to the early days of C, when computers were slow and performance was of the utmost concern. C opted to intentionally leave the size of an integer open so that the compiler implementers could pick a size for the int that performs best on the target computer architecture. That way, programmers could just use int without having to worry about whether they could be using something more performant. By modern standards, the lack of consistent ranges for the various integral types sucks, especially in a language designed to be portable. Fixed width integers. To address the above issues, C++11 provides an alternate set of integer types that are guaranteed to be the same size on any architecture. What? Because the size of these integers is fixed, they are called fixed width integers. Fixed width integers are defined in the cdint header, as follows. Okay. Here's an example. We included, here's the IO stream, input-output stream, and this is the cdint, cstdint. Why? It's, okay, so we're calling something so that integers can be used on any architecture. This library is being called for that purpose. X is always 32-bit, so that'll always fit. Okay. Best practice. Use a fixed width integer type when you need an integral type that has a guaranteed range. Warning. Standard int8 type and standard uint8 type typically behave like characters. Oh, the u is like unsigned int and then unsigned int. Due to an oversight in the C++ specification, modern compilers typically treat standard int8 type and standard unsigned int8 type and the corresponding fast and least fixed width types, which we'll introduce in a moment, the same as signed characters and unsigned characters respectively. Thus, on most modern systems, the 8-bit fixed width integral types will behave like character types. I think this needs to be the last lesson. I'm like tripping up. As a quick teaser, initialize 8-bit integral type with value 65. Probably expecting this to print 65. Although you're probably expecting it to print 65, it probably won't. We discuss what this example actually prints and how to ensure it always prints 65 in lesson 4.12, Introduction to Type Conversion and Static Cast, after we cover characters and how they print in lesson 4.11. Warning! The 8-bit fixed width integer types are often treated like characters instead of integer values. This may vary per system. The 16-bit and wider integral types are not subject to this issue. My freaking nose, dude. For advanced readers, the fixed width integers actually don't define new types. They are just aliases for existing integral types with the desired size. For each fixed width type, the implementation, the compiler and standard library, gets to determine which existing type is aliasized. I don't know what that word is. Allied? I don't know. As an example, on a platform where int is 32 bits, int32 type will be an alias. It is aliased. existing type is aliased. Okay. As an example, on a platform where int is 32 bits, standard int 32 type will be an alias for int on a system where int is 16 bits and long is 32 bits. Standard int 32 type will be an alias for long instead. So what about the 8-bit fixed width types? I don't understand any of this. In most cases, standard int 8 type is an alias for signed character because it is the only available 8-bit signed integral type. Bool and character are not considered to be signed integral types. And when this is the case, standard int 8 type will behave just like a character on that platform. However, in rare cases, if a platform has an implementation specific to 8-bit signed integral type, the implementation may decide to make standard int 8 type an alias for that type instead. In that case, standard int 8 type will behave like that type, which may be more like an int than a character. Standard unsigned int 8 type behaves similarly. Other fixed with downsides. Oh my gosh. My nose. Fixed width integers have some potential downsides. First, the fixed width integers are not guaranteed to be defined on all architectures. They only exist on systems where there are fundamental integral types that match their widths and following a certain binary representation. Your program will fail to compile on any such architecture that does not support a fixed width integer that your program is using. However, given that modern architectures have standardized around 8, 16, 32, 64-bit variables, this is unlikely to be a problem unless your program needs to be portable to some exotic mainframe or embedded architectures. Second, if you used a fixed width integer, it may be slower than a wider type on some architectures. For example, if you need an integer that is guaranteed to be 32 bits, you might decide to use a standard int 32 type, but your CPU might actually be faster at processing 64-bit integers. However, just because your CPU can process a given type faster doesn't mean your program will be faster overall. Modern programs are often constrained by memory usage rather than CPU, and the larger memory footprint may slow your program more than the faster CPU processing accelerates it. It's hard to know without actually measuring. These are just minor quibbles though. Fast and least integral types. Optional. What? Like optional to learn? To help address the above downsides, C++ also defines two alternative sets of integers that are guaranteed to exist. The fast types, standard int fast type and standard unsigned int fast type, provide the fastest signed unsigned integer type with a width of at least number bits, where number 8, 16, 32, or 64, for example, will give you the fastest signed integer type that's at least 32 bits. By fastest, we mean the integral type that can be processed most quickly by the CPU. The least types provide the smallest signed unsigned integer type with a width of at least number bits, where number is 8, 16, 32, or 64. For example, unsigned int least 32 type will give you the smallest unsigned integer type that's at least 32 bits. Here's an example from the author's Visual Studio 32-bit console application. This produced this result. Bits. There's some bits. You can see the standard int least 16 type is 16 bits, where standard int fast 16 type is actually 32 bits. It's because on the author's machine, 32-bit integers are faster to process than 16-bit integers. As an example, let's assume we're on an architecture that has only 16-bit and 64-bit integral types. Standard int 32 type would not exist, whereas standard least int 32 type and standard fast int 32 type would be 64 bits. However, these fast and least integers have their own downsides. First, not many programmers actually use them, and a lack of familiarity can lead to errors. Then, the fast types can also lead to memory wastage, as their actual size may be significantly larger than indicated by their name. Most seriously, because the size of the fast least integers is implementation defined, your program may exhibit different behaviors on architectures where they resolve to different sizes. For example, wraparound. Intentionally overflow to invoke wraparound behavior. This code will produce different results depending on whether standard unsigned int fast 16 type is 16, 32, or 64 bits. This is exactly what we're trying to avoid by using fixed width integers in the first place. Best practice. Avoid the fast and least integral types because they may exhibit different behaviors in architectures where they resolve to different sizes. Best practices for integral types. Given the various pros and cons of the fundamental integral types, the fixed width integral types, the fast least integral types, and signed unsigned challenges, there is little consensus on integral best practices. Our stance is that it's better to be correct than fast, and better to fail at compile time than runtime. Therefore, if you need an integral type with a guaranteed range, we recommend avoiding the fast least types in favor of the fixed width types. If you later discover you need to support an esoteric program for which a specific fixed width integral type won't compile, then you can decide how to migrate your program and thoroughly retest at that point. Dude. Best practice. Prefer int when the size of the integer doesn't matter. The number will always fit within the range of a 2-byte signed integer. For example, if you're asking the user to enter their age or counting from 1 to 10, it doesn't matter where the int is 16 bits or 32 bits, the numbers will fit either way. This will cover the vast majority of the cases you're likely to run across. Prefer standard int type when storing a quantity that needs a guaranteed range. Prefer standard unsigned int when doing a bit of manipulation or well-defined wraparound behavior is required. For cryptography, is that the word? Or random number generation. Avoid the following when possible. Short and long integers. Prefer a fixed width integer type instead. The fast and least integral types. Prefer a fixed width integer type instead. Unsigned types for holding quantities. Prefer a signed integer type instead. 8-bit fixed width integer types. Prefer a 16-bit width integer type instead. Any compiler-specific fixed width integers. For example, Visual Studios defines int 8, int 16, etc. Holy shit. What is standard size type? Consider the following code. I gotta do it. Spell it right?
Hello. Today on Consider the Following, I'd like you to consider the following.
Consider the following code. Size of int. On the author's machine, this prints 4. Pretty simple, right? We can infer that operator size of returns an integer value. But what integral type is that return value? An int, a short? The answer is that size of returns a value of type.
Consider the following.
Consider the following. Standard size type is an alias for implementation defined unsized integral type. In other words, the compiler decides if standard size type is an unsigned int, an unsigned long, an unsigned long, etc. Key insight. Standard size type is an alias for implementation defined unsigned integral type. It is used within the standard library to represent the byte size or length of objects. For advanced readers, standard size type is actually a type def. We cover type defs in lesson 10.7, type defs and type aliases. Standard size type is defined in a number of different headers. If you need to use standard size type, I don't know what that is, CSTD at def is the best header to include. Okay, header. It's a header. As it contains the least number of other defined identifiers. Okay. Best practice. If you use standard size type explicitly in your code, include one of the headers that defines size type. We recommend CSTD def. Using size of does not require a header, even though it returns a value whose type is standard size t. Much like an integer can vary in size depending on the system, standard size type also varies in size. Standard size t is type is guaranteed to be unsigned and at least 16 bits, but on most systems will be equivalent to the address width of the application. That is, for 32-bit applications, standard size type will typically be a 32-bit unsigned integer. And for a 64-bit application, standard size type will typically be a 64-bit unsigned integer. Size of operator returns a value of type. Standard size type. Author's note. The following sections are optional reading. It is not critical that you understand what follows. We're gonna do it. We got this. Amusingly, we can use the size of operator, which returns a value of type standard size type, to ask for the size of standard size type itself. Compiled as 32-bit 4-type console app on the author system it prints 4. Standard size type imposes an upper limit on the size of an object. The size of operator must be able to return the byte size of an object as a value of type, standard size t. Therefore, the byte size of an object can be no larger than the largest value that standard size t can hold. C++ 20 standard, basic compound, says that constructing a type such that the number of bytes in its object representation exceeds the maximum value representable in the type standard size type is ill-formed. If it were possible to create a larger object, size of would not be able to return its byte size, as it would be outside the range that a standard size type could hold, thus creating an object with a size in bytes larger than the largest value of an object of type. Standard size type can hold is invalid and will cause compile errors. For example, let's assume that standard size type has size of 4 bytes on our system. An unsigned 4-byte integral type has range 0 to the shit ton. Therefore, a 4-byte standard size type object can hold any value between 0 and 4 billion. Excuse me. Any object with a byte size of 0 to 4 billion could have its size returned in a value of type standard size type, so this is fine. However, if the byte size of an object were larger than 4 billion bytes, then size of would not be able to return the size of that object accurately, so the value would be outside the range of the standard size type. Therefore, no object larger than 4 billion bytes could be created on this system. Oh my god, there's the end. As an aside, the size of STD size type, standard size type, imposes a strict mathematical upper limit on an object size. In practice, the largest creatable object may be smaller than this amount, perhaps significantly so.
Some compilers limit the largest creatable object to half the maximum value of standard size type. An explanation for this can be found here. Other factors may also play a role, such as how much contiguous contiguous memory a computer has available for allocation. When 8-bit and 16-bit applications were the norm, this limit imposed a significant constraint on the size of objects. In the 32-bit, 64-bit era, this is rarely an issue and therefore not something you generally need to worry about. Oh my god, dude. All right. Shit. Okay. I'm like, do I even want to do this? Yeah, let's do it. I feel like I was doing better than I was expecting going in. I don't have a hydrate. I just have Diet Pepsi. Okay. Get on the B. Okay. Am I going? Go. Oh, fuck. We're already in it. Shit. Come on. Shit. Okay, we're doing worse. I felt better at the beginning of the stream and it started going downhill, so it's not gonna be better. I don't know why I thought it would be. Yo, we're never gonna get through this. Does this exist? Okay. Holy. Okay. Let's calm down. I'm trying to like rush through it and it's taking me longer. Oh, look at that. I'm just calm down. Oh, fuck. Bro. Phew. No! Cute. Holy shit. Got this. I'm not meant to hit the backspace button, but no. I need to have the muscle memory of like, oh, I typed that wrong. Rewind. Ooh.
We're getting there. Alright, last one. Fuck. Kill me. Okay. Oh my god, dude. Hit the Windows key. Fuck it. We're looking. Okay, that was better. That actually was a little better, I think. I think we got 12. Now it's 14. Alright. We did it. We did it. I've been very nervous to like come back to this. I was like, you know, just kind of need to jump in. We'll get back into the groove of it. Okay. Looks like was it? It was good. Yeah, let's just do a easy middle raid. There's our raid message. Okay. I'm gonna send you guys off. That was good. We're gonna be back tomorrow. We're gonna do some more sims because we need to get that down. We need to get that figured out. Yeah, I don't know. I'm just gonna send you guys out. Thank you for being here and hanging out and learning with me. Bye.